And the next presentation is by Henk van Hardeveld, and the title is Zooming in on CO2 emissions of adaptive peatland management. And Henk, you work at the water board, so we get now the perspective of the water board. Great.
Thank you.
The floor is yours.
Actually, we prefer to call ourselves Regional Water Authority, like Martijn mentioned, because waterboarding is a hobby of the CIA. We don't engage in that. So, having said that, I will be zooming in on CO2 emissions, but I also will be zooming out of CO2 emissions. Gilles didn't know that yet, because it's not in the program, but a few years ago we next. Technology, yes, there we are. A few years ago we wrote an original paper on integrated assessment of adaptive management strategies in Dutch peatland polders. And that's really the start of the zooming in point. So I like to zoom out first, and halfway through my talk I will zoom in. Now the challenge we are facing is how to arrest and reverse unsustainable peatland management. And we address this challenge from a context of experiments with higher water levels, with field drains on polluticulture, experiments that have been going on in the Netherlands in the last few years. Experiments went pretty well, pretty good, but what was still unknown is, well, a clear understanding how to implement these local experiments into large-scale real-world settings. So what we thought, it's easy. You just need to know everything that concerns everybody and very accurately as well. So let's do that. Let's make an integrated assessment of time and place specific peatland conditions and feasible management options with a fair distribution of costs and benefits. That's very important as well. You can read all about it in this paper we wrote a few years ago. I will present the highlights today. Starting with our approach, we used the repeat template on the Tiger and Geo design platform to make an integrated assessment of water management strategies starting now until the end of the century. We considered business as usual, traditional water level management. Water levels are maintained 30 to 70 meters below the soil surface, adjusted for soil subsidence every few years. And then a second strategy in which the levels become progressively higher because we will never change them again. We'll just fix them at the current level. And the third one is reflects the experiments with field drains. It's a novel application in which the groundwater table is maintained 45 centimeters below soil surface, and the levels are not adjusted. So, for all these scenarios, we assessed the water levels, groundwater tables, soil subsidence. From that we derived the greenhouse gas emissions, and we needed to consider the costs and benefits as well. So we also included net value added, agriculture, management costs, the damage of real estate, and we also considered the impacts of ecology in ditches. I'm not going to show you all the results, only these maps of the main results. They show the soil subsidence in the until 2100. And on the left hand side you see the map of the business as usual situation with red patches that exceed 1 centimeter of soil subsidence a year due to the oxidation of the peat. And on average it's about 2 centimeters in 3 years, give or take. The second scenario with the progressively higher water levels, it shows some changes, but not really all that much, because it's a really slow process. At the end of the century, the rate of soil subsidence will have been diminished, but in the years to come, changes are limited. You cannot say that for pressurized field drains, because in one go, the subsidence rate is very markedly diminished. So this is a very effective strategy. You can also see that in these graphs. On the left-hand side you see the blue line. That's the business as usual. Soil subsidence 2 centimeters in 3 years. And the green line pressurized field drains only a few millimeters a year. So it's very significantly. On the right-hand side, you see the greenhouse gas emissions. And of course, with these rates of soil subsidence, the CO2 emission is markedly lower. So that's good news. And there's more good news, because the net value added of agriculture is at a constant high level. There are less management costs. In fact, all seemed well. You only need to tackle the implementation costs, around 425 euros per hectare per year, give or take. It depends if you choose for a low end or a high end technology. And well, it's too much for a water authority or for a farmer to pay up by itself. But if you consider it in the scope of mitigating climate, the Paris Agreement, the national government maybe can grant a subsidy, and then it will cost around 40 euros per ton of CO2 equivalent. And some people told me that's pretty much a bargain. So we all lived happily ever after. Except that we didn't. Because to implement this, you need to know everything for everybody very accurately, and there was something wrong. There was something wrong with the science about soil subsidence and CO2 emissions. And take a quick look around. I'm very glad Jan van Akker is not in the room, because well, we used an adaptation of a linear regression between soil subsidence and groundwater tables that Jan and his colleagues designed over a decade ago. And actually a pretty good, well-founded regression, except it doesn't reflect very wet conditions, and it also doesn't reflect conditions with field drains. So there was a lot of controversy among scientists. Can you use this? Yes, you can. No, you can't. And people became angry at each other, and then the science started to build up, and there were some examples where the implementation of field drains did exactly what the regression of Jan van Akker predicted, but also examples where it did something totally different and nobody could really understand it. So we had to start a big program with monitoring and modeling. In fact, the program Gilles is chairing, NOBV. And well, one of the things they are considering, it's from our German colleagues, Saurig and her colleagues. They demonstrated a few years ago that when you zoom in on the topsoil in the peat, then you see a nice parabolic relation between the emission of CO2 and soil moisture. And a parabolic relation is something totally different than that linear relationship. So that's a clue why things are so differently. And then Jim Bowman and his colleagues last year, they presented a paper in which they designed a totally new method called the Somers method. Maybe you can help me out, Gilles, where it stands for. It's an acronym.
Subsurface Organic Matter Emission Registration System.
Yeah.
I can read it.
Quite a mouthful, but it's very sophisticated. I like this method very much. And it takes into account all these processes, parabolic relations with soil moisture. It takes into account the temperature, and takes into account all the measurements that were taken over the years. And as you can see, then you have two directories, one that's applicable for regular conditions and one that's applicable for conditions with subsurface drainage. So, great. Now we can move on. What we did, we incorporated the Somers method on the Tiger and Geodesign platform, the platform that we use for the integrated assessments. And we compared. What did we see? On the top you see the Somers maps, and on the bottom you see the repeat maps. This is another polder. We have a lot of polders in the Netherlands, so we picked another one. On the top end, I think this is that's the nice thing. This is what SOMAS tells us. There's some, even with pressurized field drains, there is some emission, about 5 ton a year, give or take. What we repeat with the Jan van der Akker question would tell you that there is no emission at all. It's a bit overly optimistic. We didn't trust that to start with, and I think the SOMAS method predicts it much, much better. That's good. There are all, some things are not quite as good yet. Here you see these patches that are very deep orange, turning red, and SOMAS doesn't show that. That's because SOMAS, the 0.1 version of SOMAS, only considers the water level in the ditches and not groundwater levels. And the repeat Jan van Akker regression does consider groundwater. So if you have strong seepage or thick clay deposits on top of your peat, the old method was still a bit better. So in the short term, what we are doing now, we use both, and we explain the differences, and we have a discussion about the uncertainty. And hopefully in the slightly less short term, maybe even later on this year, when there's a new version of SOMAS, which does include groundwater, then we can just switch to that. So prospect look good. Which brings me to the conclusions. Fortunately, adaptive management can slow down soil subsidence, CO2 emissions with higher levels, field drains, maybe a bit of polluticulture. We can come a long way with that, so that's very good. Pressurized field drains can still be a part of the implementation pathways. Not everybody will sing hallelujah just like I told you in the first place. There are some downsides. It's not as effective as we first thought, but still it's very effective. So it can be a part. SOMAS method is available, very well suited for the CO2 assessments. Improving still, the repeat is available, very well suited for integrated assessments. Improving still, so we're good to go. And soil subsidence science won't be the bottleneck for this implementation process. But I'm not cheering just yet. We're not there just yet. We need to zoom in on some other aspects as well. Not today, but maybe next TISOLS episode. Water quality and biodiversity is very important. When you re-wet the peat soils, it might lead to a lot of flushing out of nutrients. So how to deal with that? There need to be a viable, sustainable business model for agriculture. It's now focused on bulk production, very as cheap as possible. It's not sustainable. Well, how can you change that? And last of all, we need to really embrace collaborative processes. This is what happened in the Netherlands when the government tried to enforce top-down a decision about nitrogen. The whole country was, taken hostage by the farmers. In fact, one of the tasks of a regional water authority is to prevent things like that and to do a better job, to put it shortly. Well, that's it for now. Thank you for your attention. If you have any questions, ask them.
Thank you, Henk, and for not blaming us to be the limiting factor. That's, but you're a scientist as well. I should say that with your history. Any questions from the audience? Pietro.
Okay, thank you. Very nice presentation. I have one question about this pressurized drain. How they work? So I can imagine you use fresh water and you push fresh water into this drain that you put into the field. But this means that you need a lot of fresh water to do this. And is this something that is available
Ah.
And yeah, also taking into account, I don't know, in Italy we have during summer very huge shortage of fresh water availability. And so we need mainly this during summer when we have hot temperature and when oxidation is an issue, right? So is this something that you also taken into account, let's say, in terms of climate change and very dry summer, very hot summer? I think also in the Netherlands is going on.
Yeah, that's a very, very good question. I think it's one of the main topics we're working on right now. You can see here the tubes are being installed into the ground, and at the end there's a big collector vessel in which you pump water from the ditches into the vessel, then it flows into the ground. And yes, it takes up more water than currently. The amounts vary. Most of them think about 20-25% more water during summer. On some locations it can be even bigger, more than that, but well, we're zooming in on that as well. There's something going on there. Do we have it available? Yes and no. Overall, we have pretty much fresh water in the Netherlands in our big rivers, but we have increasingly less, and the demands are increasingly higher. So yes, it is a problem, and we are frankly not quite sure how to tackle this most eloquently. Maybe in the next episode of TISOLS I can tell you all about it.
Great. Further questions? Henk. Yeah.
Yes, thank you very much for the very nice talk. I have two short questions. You showed us an average soil subsidence for the three different water management, and I'm not sure if you told us, but I wondered how you calculated those average soil subsidence. And the second question is about the pressurized field drains on this figure. We have the small spot in the middle with low water levels, and I just wondered what that is.
Two good questions. How we calculated this, we have a simple but effective hydrological model, which takes into account the impact of surface water level on groundwater levels. And then we use the relation of Van den Akker, the linear regression model, to convert the groundwater levels to soil subsidence rate. And then there's a time series also taken into account the increasing temperatures of climate change. So that's how we calculate it. The red spot on the right hand side, it's a small village in which soil subsidence, the field drains are not applied.
There's time for one last short question. If not, yeah, sorry, yeah, and a short answer.
So I understand the CO2 that you believe is emitted by lowering the groundwater. So that's largely based on models, right? Is that correct? Or can you also do measurements to verify your models?
Yeah, we are doing a lot of measures to verify the models with the eddy correlation mass and chambers on the ground. So the SOMAS method is very much validated with those measures.
Thanks.
Okay, thank you very much, Henk. A big round of applause, please, for Henk.